have a caravan. It consists of 10 cars in this caravan. Okay, there are 10 cars in this caravan, and this caravan wants to pass 100 kilometers between two pay-tool or gateway in a highway. Okay, there is a highway. Its length is 100 kilometers, and our caravan decided to pass this highway. Let's suppose that during each 12 seconds, one car can pass the pay tool and enters to the highway. Okay, so we need 12 seconds to service and to pass the first gateway here, okay, to enter into the highway. And in the highway, our speed is 100 kilometer per hour. Speed of each car is 100 kilometer per hour. Okay, so the question is this. The end time is the time that the last car in caravan exits from the second gateway. Okay, how long it will take from us? As we know, the length of this highway is 100 kilometer. Car is 100 kilometer per hour. So simply I can say that each car should spend one past one. And yes sir, you are welcome. All of you can join to the first group or the second group always during the term in my course. It doesn't matter. You can join freely. Okay, don't worry. Also, you, Muhammad Hassan, you are welcome too. Okay, so each car will spend 1 hour or 60 minutes to pass the highway, but we have another time too. We need another time too. As we say, each car needs 12 seconds to pass the first gateway. We have 10 cars, so we need 120 seconds we need to extra 120 seconds to service the whole caravan, all of those 10 cars, to pass the first gateway. So totally we need 62 minutes to pass this caravan from this highway. 60 minutes for each car to pass the highway, and 2 minutes to pass this gateway, the first gateway. So totally we need 62 minutes for this. Here, in this example, we can say that, okay, car 1 is similar to packet, network packet, and cars are similar to bits or bytes. So here we have a 10 car 1, it's similar to a 10 byte packet or 10 bit packet or something like that. Okay, and as we say, each car can goes with the speed of 100 kilometer per second per hour. It's similar to propagation speed in the networks. Or we say that, okay, we need 2 extra minutes to put the car 1 on the highway, passing the first gateway. It's similar to transmission delay in computer networks. Okay, so we can see everything in computer networks is similar to our real world. It's not something strange. Let me make some changes in the example. Let's suppose that the propagation speed or the speed of each car in the highway increases to 1000 kilometers per hour. The last one was 100 kilometers per hour, and here we suppose that each vehicle can go with a speed of 1000 kilometers per hour. So we increase the speed 10 times. Okay. And also, each vehicle needs to spend 1 minute in the first gateway. The service time in the first gateway for each car is 1 minute. So here we can ask another question. Okay, will car arrive to second booth before all cars service at the first booth? In another word, when the first car leaves the highway, it reaches to the second gateway and leaves the highway. Okay, when the first car leaves the highway, which of those cars in the car 1 will enter into the highway? Which of them? Here, as we said, each vehicle needs to take 1 minute spending in the first gateway. And here, the length of this highway is 100 kilometers, and the speed of cars is 1000 kilometers per second. So each car, we can say that each car only needs 1/10 of minute, 1/10 of hour, or 6 minutes. Each car needs to spend 6 minutes to pass this highway. The length is 100 kilometers and the speed is 1000 kilometers per hour. So each car needs 1/10 of hour or 6 minutes to pass this highway. So we can say, okay, when the first car arrives to the second gateway, the 7th car in the car 1, the 7th car will enter into the gateway and into the highway. the seventh car will arrive to the highway. What does it mean? It means that if I increase the propagation speed in the network, I will increase the size of this car one, the distance between different cars. In computer networks, if I increase the propagation speed in a network, I will increase the size of each packet in that network. Also, you can see here, in the first example, the propagation speed was 100 km per hour, and each vehicle spends 12 seconds in each gateway. And now I increase the propagation speed to 1000 km per hour, and each vehicle needs to spend 1 minute to get a service in the first gateway. So when we increase the speeds in the computer networks, in the communication links, it's trivial that we increase the size of packets too. This is an interesting properties in communication links. As soon as increasing the speeds in communication links, you will increase the size of packets too. Naima, yes, Naima. In the first example, each vehicle spends 12 seconds. No, each vehicle spends 12 seconds to pass from the first gateway. In the pay tool, in highways, in the pay tool, you should stop the car and pay some fees, and then the gateway will be open and you can pass the gateway. Okay. In the first example, we suppose that each vehicle spends 12 seconds to do this, paying fees and paying money and passing the gateway. In the second example, we suppose that each vehicle spends 1 minute to do this. Okay? And one main point and main interesting properties in computer networks, in all of networks. Let's suppose that in a network, in a communication link, on average, a packet will arrive to, for example, a router, a switch, I don't know, a point, a communication platform. A packet, on average, a packet will arrive to a node, to a network node. Okay, and those packets, on average, those packets have lengths of L bit. Each packet has L bit length. Okay, and the bandwidth of the link is R bit per second, or the transmission rate of the link is R bit per second. We define traffic intensity as this: L times in A divided by R. This is traffic intensity. In other words, we say that traffic intensity is the arrival rate divided by the service rate. What does it mean? Look at this chart here in the right side. If the traffic intensity is low, is something near to zero, we can see that the average queuing delay is near to zero. As soon as the traffic intensity increases, you can see that the queuing delay will increase too. It will increase. But here, look at the right side of this chart. You can see from some points, as soon as we increase the traffic intensity, the queuing delay will rise exponentially. When something like this happens, it's simple. When the traffic intensity moves toward the 1, it means that the arrival rate is something near to the service rate. So you can see here that the queuing delay will rise exponentially. We can sense this effect in our daily life. How? For example, if you go to bank, you had something to do in bank, and you are going to bank. If you go to bank in the morning, very soon in the morning, you can do your job, your task very soon, just in a few minutes. Okay? But if you go to bank near the noon, for example, 11 o'clock, 12 o'clock, something like that, you can see that you must spend half an hour or maybe greater than this. You need to spend lots of time in the bank to get your service. Why this happens? Because in the morning, the bank is empty. There is no customer in the bank, so you are standing in an empty queue or in a queue with small length. So according to this chart, the traffic intensity in the bank is low, is near to zero. So you spend a few minutes to get your service. But in the noon, the arrival rate of people to get service from the bank will increase. But we know that the service rate in the bank does not change. So something like this happens. You need to spend 2 many times, maybe half an hour, maybe 1 hour, or maybe more than this to get your service. So this property is very important. Why? We can see that if all communication links became congested, it means that the traffic intensity at that link is close to 1. It means that the length of queue rises and we need to spend more times in the queue. The queuing delay would be increased too. So this is an important properties in computer networks. Why? Because sometimes we have very special applications. Those applications cannot tolerate line delays. So maybe we should do something else. For example, look at this image here, these pictures in the right corner side. In one of them, you can see a road, an empty road. There's no one in that road, but in the lower image, you can see a congested road. In a congested road, you can see that those vehicles cannot move very fast. They are moving very slowly. This is the effect of traffic intensity. Here, in the second picture, the traffic intensity is near to 1 or maybe larger than 1. Yes. NTSR says that is it necessary to specify a speed or rate or delay? Yes. When I'm signing a contract with my ISP, there is something special in my contract. We call it SLA or Service Level Agreement. In that agreement, the company says that, okay, I will guarantee your service rate like this, your delay like this, your packet drop rate like this. But let me know your requirement. I'm saying, okay, my requirement is, for example, a transmission rate of 1 megabit per second. They put my requirement in the agreement, in the contract, and say, okay, we will guarantee your service. We will give you this transmission rate with this delay, with these conditions. And if the ISP couldn't answer to my requirement, they should pay penalty. I can ask them for penalty. Why? Because they couldn't act based on the agreement. So it's very important for us. Okay? They pass over the contract, so they have to pay some penalties to me. So if I be an administrator on that ISP, I should be clear about these items, about traffic intensity and something like that. General Fazil says that there is no sound. What about the other? Can you hear my sound? My voice? Okay. So then please leave the room and enter again into the class. Okay, I will prepare some extra materials about the calculation, how we can calculate the queuing delay in computer networks, in links, in different links. I will prepare a good example for you, and I will record it in the next session, inshallah. Okay. Okay. I missed these slides in the chapter 1. I'm sorry again. I apologize for them. Have you any question about these content in chapter 1? If you have question, please ask me. Okay. I'm going to chapter 4. Okay. This week we are busy. Some of the students are busy, so I will extend the time of exam in chapter 1 1 week. Okay, instead of having exam in October 17. Oh yes, October 16, excuse me. We will have the exam on October 23rd. Okay, I will show you about the Wireshark. I will give you your needed information about the Wireshark project. I will give you the whole things. Okay, don't hurry up. This week I will ask you to do your Wireshark homework, and next week you can read the book to prepare for your final exam from chapter 1. After that exam, we will remove chapter 1 from all course. You know, Hannah, in this term, after finishing each chapter, I will take an exam, and that exam have some scores. After that, I will remove that chapter from your course. We will continue this strategy until the end of term. And at the end of term, I will make a summation of all of those scores, and I will give you your final score. So don't worry about the final exam. Just read the text during the term and pass the exams. Just be clear about those exams and try on them. Okay? So this week I will talk about, I will prepare information about your homework with Wireshark, and the exam of chapter 1 will be held on 1st of Aban according to Iranian calendar, 1st of Aban, or 23rd of October, or I think 16 of Rabiul Awwal in Iranian calendar. Before the birthday of the Prophet Muhammad, peace be upon him, we will have the exam. Yes, something Surah Islam. Yes, something near the something same as data mining exams. It's all of the exams would be multiple choice. exams, multiple choice questions. I will give you more information at that time, before the exam, about the number of questions and the way that you can enter into the exam and take them. Okay? But now, just read the chapter 1 completely. Okay, chapter 4 of the book is about the network layer. Here, in this course, we will read more about the network layers in 2 chapters. The first chapter is about data plan, and the second chapter and the 5th chapter, chapter 5, next chapter, chapter 5, is about control plan. We will talk about these chapters because there is something new in the content of network layer, which is important in the future of computer networks. So we will talk about chapter 4 and chapter 5 in this course. Okay. Here in chapter 4, we try to understand key principles behind the network layer, its services, and some important protocols in network layer. As we talked in chapter 1, the network layer in computer networks is the 3rd layer. Physical, data link, and the 3rd one is network layer. Okay, here we want to talk about the network layer service models, forwarding versus routing, how a router works, addressing, generalized forwarding, internet architecture, and something like that. Talking about IP protocols and how we can use NAT in this layer. Okay. If we look on network layer, in traditional network layer chapters, in traditional network computer network books, you can only see some important contents talking about data plan. But now we have something new in this layer. So we have to talk about control plan in network layer 2. We will talk about data plan here in chapter 4, and control plan will be remained for chapter 5. Okay. Also, we look into a router, into the architecture of a router, its input ports, its switching, its output ports, how it manages its buffer, what is the scheduling in a router. Also, we'll talk about IP protocol or internet protocol, its formats and addressing IPv6, and how we can translate the network access. And our specific guest, SDN and OpenFlow. This is the main and the newest topic in network layer. We have to talk about SDN, software-defined networking. Why? Because it's the future of computer networks. It's the future. So we have to talk about this, how it works, and what is, for example, OpenFlow protocol. Okay, let me talk about the services in network layer. When we talk about network layer services, as we talked in chapter 1, this layer handles the packet. We put our packets or data or segments into the network layer, and those segments are wrapped into a packet, into some packets, and the network layer is responsible to send those packets from the source to destination, from the sender to the receiver. So the network layer is a delivery responsible. It is responsible to deliver packets to the destination. Okay? And as we know, the network layer, look at this picture. As we know, the network layer is presented in the whole devices along the path, in the source, in the destination, and also in the routers. In the routers along the path in different networks. Those routers are responsible to get a packet, check the IP header, find the path toward the destination of that packet, and then modify the packet, the header of packet again, and send the packet toward that destination, toward its destination. It will receive packets from its input port, and it will pass the packets toward its output ports. So, as we said in chapter 1, the network layer has two basic functions. One of them is routing, finding a path from the source to destination. So we need routing algorithms. And the second one is forwarding. Okay? Moving packet from one router to another one, passing the packets until the destination. Receiving a packet from a source and passing it, forwarding it toward into the next hop toward the destination of that packet. If I make an analogy, I can talk about finding a path in a trip. I want to go a trip. Okay? So firstly I should find a path, and then I should move along that path toward the destination. Maybe during this path I should pass some big bridges with multiple floors and multiple ways. I don't know. So maybe, but I should care about those passes and how I can pass them toward my destination. We can divide a network layer into two different panels, two different sections. The first one is data plan, and the second one is control plan. When we talk about data plan, we talk about the basic functions of a router. We say that okay, one packet will arrive to the router, and router should define its path and forwards it toward the destination. Okay. This is data plan. How we should handle a datagram and an arrival datagram. How we should handle finding a path from the source input into the output port, from the input port toward the output port. This is data plan. Handling an arrived packet. But there is another plan, another main and very important plan. We call it control plan. It's a network-wide logic. What does it mean? It means that in control plan, we should know about the whole network, the structure of whole network, okay? And make decision how to handle different packets, datagrams, I don't know, between sources and destinations. So it means that datagram, it means that control plan is about routing. We should define a route for the arrival packets. It's something about control actions in routers. As a user, I never think about that. I don't care about them. The network should find a path for my packets. How? I don't know. I'm not care about them. But the ISP should be care about that. The administrator should be care about that. How we can find those paths? Okay, simply we can use traditional routing algorithms. For example, OSPF or RAPE, EIGRP, ISIS, I don't know. There are several routing algorithms in network nodes. We can use them. But to date, we can use software-defined networking or SDN. I told you, this is the future of computer networks. In SDN, in traditional routing algorithms, a routing protocol is started on each of routers individually. Each router has started its own routing protocols to find the passes around the network. Okay? Each of those routers will do this strategy. But in SDN, in a state of routers, we have one or two servers in the network. That servers will think about the passes, the routes in the network. That servers. Okay. talk about SDN in the future. But now we can say that in traditional algorithms, each router will run a routing algorithm, something like this. We have several routers in the network, and each of them is running a routing algorithm per router. Okay, each of them runs the routing algorithms, and the results of those algorithms is saved in a table. We call it forwarding table or routing table. So a routing table is a result of a routing algorithm. This is finding routes in a traditional computer networks. But as we said, in SDN or software-defined networking, those routers in the network just think about finding a path, finding a route using a table, a forwarding table or a routing table. But here, the control plane is shifted into some servers. Those servers think about the routes, about the passes, finding passes, those servers. What does it mean? It means that in the future routers have not control plan. Their control plan will be shifted into some routers, some servers. And those servers think about the passes, and then their result will be returned to the routers, to our routers. And our routers just consume the results. Why this is important? Because I can assign a simple server into my network and run the SDN server in that server. And then, instead of having a complicated router, I can have a simple router. Why simple? Because it does not think about too many things. Just it needs to think about forwarding. Even here, in the control plan in this remote servers, I can think about, for example, secure routing, a routing with quality of service, a routing with backup routes, everything. Using this strategy, I can handle my traffic clearly with complete control. It's different. I will check. I never think so, because these slides are version 8 of the slides are version 8 of the book. I will check it. Okay. Oh, I will prepare a link for you, but be clear. In that link, you can see slides of the 7th edition of the book and slides of the 8th edition of the book. No. Be clear about this. I'll prepare a link for you, a download link for you. Okay? In that download link, if you go, you can see a web page. In that web page, you can find slides of the 7th edition of the book, and also there is an extra link to the slides of this 8th edition of the book. Here I'm using the 8th version, 8th edition of the book, not the 7th one. If you see these differences, please check the download version. Look at this here. Look at this. These slides are slides of the 8th edition, not the 7th one. Okay. Okay. Cool. Okay. When we think about the service model of the network layer, we can say that the network layer prepare a channel to transport my datagrams from the sender to the receiver. This channel will try to deliver the packets or datagrams to the sender. Okay? But maybe someone say, okay, can it guarantee this delivery, or can it guarantee the delay between the source and destination? I should say, okay, it depends. I will ask you why it depends. But it depends. In IP version 4, we cannot guarantee these items, but it depends. For example, in virtual circuit switching networks such as ATM, frame relay, or X25, yes, we can guarantee, but in simple or IP-based computer networks, we cannot guarantee in these items. Okay. But if you look for those guarantees, we can look for something else. For example, instead of talking about individual datagram packets, we can talk about a network flow, a traffic flow. A traffic flow is a combination of some packets. Those packets have similar source and destination. Okay, a flow is a collection of packets with similar source and destination. So those packets should be sent into a similar path. It's completely clear because their source and destination are similar. So simply we can say, okay, send them into a similar. And if I send them into a similar path, so I can guarantee that those datagram will arrive to the receiver in order. And also I can guarantee a minimum bandwidth for flow and make more restriction. on sending those packets. Okay, so remember this word flow or traffic flow. Remember this, we will talk about it in the future. Look at this. In today's IP-based network, when we talk about a datagram network, or when we talk about a packet switching network, a packet switching network, something like internet, acts as a best effort system. It means that it will try according to its power. It will try to do. And inshallah, your packets will arrive to the destination. Inshallah. Okay? It means best effort. So we have no guarantee on successful delivery. We have no guarantee on time of delivery. We have no guarantee on bandwidth availability. We have no guarantee. This is best effort. Okay. So when we talk best effort means inshallah. We will do something, inshallah, we will receive a good result, inshallah. Okay? So here we never guarantee the bandwidth, the loss rate, the order between the packets, and timing. We never guarantee these items. Cannot find some slots? Why? Can you see this one? Naima, can you see this on slide 411? Oh, you mean that you cannot find the slides from different chapters? I will upload all of them for you in the WhatsApp group. I will upload all of them. Don't worry, okay? Okay, so when we talk about internet, we can see that the internet can guarantee nothing. But what will happen if I need something? Some guarantees. I will send it. Okay, I will send it. For example, let's suppose I have using ATM technology. ATM is a virtual circuit switching technology. ATM is a network with virtual circuit switching technology. Look at this. ATM has several services, several service models. For example, one of them is CBR, or constant bit rate. It means that it will guarantee a fixed bandwidth. So I can send a constant, I can send my data with a constant rate. It will guarantee the loss rate, order, and timing. Or for example, ATM has another service model. It's available bitrate, or ABR. It will guarantee a minimum bandwidth and order between packets, but it won't guarantee the loss and timing. ATM has 4 or 5 different service models. Here you can see only 2 of those models. service models. Okay, but you can see ATM can guarantee some things. It depends to your requirement. We can use those service models. Okay, but for example, today's if we use integrated services or IntServe, or if you use DiffServe, we can guarantee some items in computer networks. For example, if we use IntServe, we can guarantee the bandwidth, loss, order, and timing over the internet. We said that the internet, the basic of this internet is best effort. So I cannot guarantee. I can guarantee nothing. Okay? But if I use IntServe, I can guarantee everything over the internet. Or even if I use DiffServe, possibly I can guarantee some items. Yes, Naima. Naima said that, okay, ATM is it transportation technology in telephone communication companies? Yes. We have two different ATMs. One of ATMs is, you can see one of those ATMs in banks. It means automatic teller machine. Teller is an employee in bank who pays the money. Okay, ATM in bank is automatic teller machine. This machine pays money to us. Okay, but here ATM is for a synchronized transfer mode. Is a telecommunication technology. We can see this technology in telephone companies. Yes. But it's absoluted. ATM is absoluted. Most of telecommunication technologies are absoluted in today's. Okay? So, again, our internet is a best effort service. Why? Because in internet we very look for a simple mechanism to transfer data over the internet. Just we need to simple transmission mechanism. Okay? If you look on telecommunication networks, telephone telecommunication networks, they are very complicated, extremely complicated. But the best effort service of internet of IP, it's very easy, very easy. You can develop it widely. But if you need to guarantee some parameters, for example, guarantee the bandwidth for this application, this Adobe Connect application. We have some strategies, some methods such as IntServe or DiffServe to provision a bandwidth, a sufficient bandwidth for a user, especially when the users need some guarantees when they are working with real-time applications such as interactive voice, videos, distance learning, and something like that. Okay. So in internet, we try to be good enough. For the most of times, we try to be good. We never guarantee internet will never guarantee those items, but we try to be good enough. And by distributing the contents among different data centers or different content provider networks all around the world, we can see the distance between the source and destination, between me and the server that I'm looking for that. This all distance will be short. I can receive the services from different locations. Okay. In today's network, the ISPs and the content provider networks try to be close to the users, to remove long distances between them and their users. Okay, and also we have congestion control mechanisms, different congestion control mechanisms to application who has elastic behavior. Elastic means that those applications can tolerate some delays, some packet losses. We can tolerate some bad news, something like this, such as this. Okay. But still, we care about this. But still, it's hard for us to argue with the success of best effort service model. It's hard. It's try to be good, but nobody can guarantee this. We care about this. Okay, that is enough for today. Is there any question? Any question? Okay, thank you. I wish the best for you in the rest of this speech, and goodbye.